So now we're going to learn some nomenclature. And the nomenclature that we do in organic chemistry is a lot more involved than what we learned in foundations. And so we start here at this point just looking at the nomenclature for alkanes. Over the rest of this course, we'll learn nomenclature for many of the other functional groups: alkenes, alkynes, aldehydes, ketones, alcohols, and others. But whether you get those and whether those make sense all depends on learning your nomenclature of alkanes. The nomenclature for alkanes forms the basis for the nomenclature of all of the other functional groups. So make sure you get a good grasp on this here so that when we get to the other functional groups, they're more straightforward. With that is also, we want to say that the nomenclature is very systematic. There's a very distinct set of rules that we use and that we follow. And anytime we need to name an organic molecule, we follow that set of rules and that set of steps. So the system of nomenclature we use is referred to as the Iupac system. And what does that mean? So Iupac is the International Union of Pure and Applied Chemistry. And they've devised this system of nomenclature that is what we use for naming organic molecules. Now, we'll just be learning the basics of organic nomenclature, because the Iupac book of organic nomenclature you can see just the beginning here of it. This is you can see the title, The Nomenclature of Organic Chemistry, Iupac Recommendations and Preferred Names 2013. So they do update and revise this from time to time. But the entire book of nomenclature, and again, this is just organic molecules. Just under 1,600 pages. Who would have ever guessed you could say that much about nomenclature? But we're going to start with some basics. And the basics that we're going to start with is that you can't do any organic nomenclature until you've learned your unbranched alkanes. So these are just our alkanes that are straight chains and have nothing else coming off of them. So here's the first 10. Obviously we can keep going. We can keep going as many carbons as you can draw. But this is a list of names that we just need to memorize. And actually once we get above 4 they get pretty easy. But we start methane, ethane, 3 carbons is propane, 4 carbons is butane, 5 is pentane. So once we get to 5, you can see we start to use the types of prefixes you're used to with numerical. So what do you think 6 is? Hexane, heptane, octane, nonane, and decane for 10 carbons. So that's the first piece. That's the basic piece that we need. Again, we can't do any other nomenclature without knowing the names of our unbranched alkanes. Those are the basis for all of organic nomenclature. Now, most organic molecules are not this simple. They're much more complex. So how do we start taking that into account? And how do we start putting those in? So again, we're going to start simple. So here's a 4-carbon chain. And we have a 1-carbon substituent, or a 1-carbon branch. So by substituent, we're talking about any group that comes off of the primary chain. So we have to have a name for this group. Well, we look at the number of carbons. This has 1 carbon. If we go back to our previous slide, if we had a 1-carbon molecule, we'd call it methane. But we can't quite use methane here, because methane assumes that it's CH4 by itself. This isn't CH4, this is CH3. And so what that means is we modify the name slightly. And we do that by chopping off the ANE and adding YL. So this 1-carbon substituent is referred to as a methyl. What if our substituent's a little bit longer? So again, here you can see we have this long chain here, and coming off of it, we have a 2-carbon substituent. Well, 2-carbon molecule, we previously said we'd call it ethane, but now, given the substituent, we do the same thing we did with methane. We chop off the N, the ANE, and add YL, and call it ethyl. And we could do that for any number of carbons. So a 3-carbon substituent would be propyl, 4 carbons butyl, and so on. But that assumes that the substituents themselves are straight chains. And that's not always the case. So we're not going to deal with really complicated substituents in this course. We'll look at a couple specific ones that are important, but we're not going to get into cases where we have substituents of substituents of substituents. They're not necessarily that difficult to do. It's just, it goes way beyond the scope of what we need in this course. So here we have a 3-carbon substituent, which we said we called propyl. But what if instead that 3-carbon substituent was connected at the middle carbon as opposed to the end carbon? Does that change the substituent? The answer is yes. We've talked about before that if you change the way a molecule is connected, it changes the function of the molecule. So we have to distinguish between this 3-carbon substituent that's connected in the middle from the one that's connected at the end. So this is known as an isopropyl. When it comes to 4-carbon substituents, there's actually 4 ways to do that. And so I'm just going to use R, where R is the main chain, and show the substituent coming off. So there we have 4 carbons in a straight line as the substituent, and that's going to be the easy one. Why is that the easy one? Butane made into a substituent becomes butyl. So that one's pretty logical. Now we could also connect at the 2nd carbon of the butyl chain. And we call that sec-butyl. We could also have a branch at a later carbon within the butane. We call that isobutyl. And finally, we could arrange the 4 carbons in the substituent like this. And we'd call that a tert or T-butyl. Now this unfortunately ends up leading to what I think is one of the more unfortunate pieces of nomenclature that may be relevant to you at some point. So here's a chart of amino acids. And if you take biochemistry at some point in the future, you very well may have to memorize the 20 amino acids. Now, the only thing that differs in the amino acids is what the R group is. But here's the unfortunate piece to me. There's 2 of these molecules that have butyl groups as substituents. I could also point out valine has an isopropyl group. But if we look at leucine and isoleucine, they both have 4 carbon substituents. So why do I say it's unfortunate? Well, leucine has an isobutyl group as its R group, whereas isoleucine actually has a sec-butyl group. So, kind of an unfortunate piece of nomenclature. I've always assumed that the reason they were named that way is probably that leucine came first or was discovered first, and then isoleucine was determined to be an isomer of leucine, would be my take on why they're named that way. But it's still, to me, a very unfortunate piece of nomenclature. The other substituents that we're going to run into, at least right away, are halogens. And they're really easy. So if you have bromine as a substituent, it gets called bromo. Chlorine as a substituent, is referred to as chloro, fluorine, fluoro, and iodine, iodo.